Hello everyone, this is Jeon Poljong. I will explain introduction to data structures. Today I will explain chapter 4, ADT, abstract data type sorted list. This figure shows sorted type class interface diagram. The yellow circle contains private data, member variables, and also this ellipses are member functions. Okay, the member functions, which member function specifications and implementations must change to ensure that any instance or object of the sorted list ADT abstract data type remains sorted at all times. We have two functions, put item and delete item. The insert item algorithm for sorted list ADT. So first of all, find a proper location for the new element to be inserted into the sorted list. Secondly, create a space for the new element by moving down all the list elements that will follow it. Thirdly, put the new element in the list. Finally, increment a length member variable. Okay. This file shows implementing a sorted type member function put item. Okay, so the parameter is the item. So basically, we are using two local variables, mode to search boolean type and location. This is the index for enumerate info array in sorted list. Okay, so find the proper location for the new element, that is the item, the passed by parameter, whose value is the location's element value. Okay, so more to search. Okay. Okay, so location length. Okay, location initialized to 0 is less than length, means we can search more in list array, and the while loop we find it. Okay, so item compare info location. Okay, so compare to three cases, less, equal, or greater. Okay. So remember, we want to put new item in appropriate location, right? So if info location, okay, we want to search. So this and the item value we can compare. Last case, this one, the item last case. We don't need to search more. Okay, just the location is the proper location for item. Okay, and then this for loop case, we make room for new element in sorted list. Okay, so which means the location case, we want to store new item. So other case, we can move to the the end of array. Okay, so move. So which means you can see index the length of sorted list. Length. So this and index -1 is previous one. Previous one is moved to the right. Okay, so we can shift to the right. Okay, toward the end of the length, okay, location. This info length -1 is actual the end of element in the sorted list. Okay, so we move to the right, and then we make a space. Okay, and then we can put item here, and then so new item is inserted, right? So we can increase this length, okay, by 1, like this. Okay, so this comparison case, the last case, we can find the appropriate location. Otherwise, equal or greater case, we assuming this array is ascending order. Smallest one is index is 0 info array, and then okay, increasing or non-decreasing. Also, certain elements values are the same. So in the textbook case, it didn't consider this non-decreasing, but increasing or ascending order. But I would consider non-decreasing is cover ascending order. So that's why I added this one. Okay, so case equal or case greater case location plus plus. So we search an appropriate location for inserted item, this one, and then location lesser than length, still we can search more. Okay, so we can keep searching. Okay, so the little item algorithm for sorted list ADT. First, find the location of the element to be deleted from the sorted list, and then eliminate the space occupied by the item by moving up all the list items that follow it, and then decrement the length. This is the implementation of the little item. So we want to find the little item location, and then we can delete. So location initialized with the value 0, and then so we start the first element in the info array. So item will be deleted, right? So this one is compare until we find okay the location of okay the element value. So if not equal case, keep increases keep increasing the location value. Okay, and then if the equal case, this value is equal, not equal is a false, and then exit. Okay, we found the location is actually equal. So in that case, move all elements that follow deleted item in sorted list. Okay, so location +1 is current deleted location, right? +1 is to the right toward the end of info array. So that one index info is copied into the left hand side, which means deleted one, right? So deleted one is overwritten. Okay, and then the index increases, and then we can shift to the left. Okay, and then so the last the length -1 is actually the last one, but we decreases by 1 like this because we deleted the item, this one. Okay, improving member function get item. We are using a linear search. We want to find some item, but if we assuming this is a sorted list case, we can find item using get item better way in terms of time complexity. So recall that with the unsorted list ADT, we examined each list element beginning with info 0, this first element, until we either found a matching key or we had examined all the elements in the unsorted list. how can the searching algorithm be improved for sorted list ADT? The answer is if info array are sorted ascending order, we can use binary search. So retrieving Elliot from a sorted list, for example. So Assad, Bradley, Hessing, Maxwell. So the names, all right, so ascending order, alphabetically ascending order. The sequential search for Elliot can stop when hashing has been examined. Okay. However, if we are using binary search in a sorted list, time complexity can be reduced from big O n to log 2n. Okay, so examines the element in the middle of the array. Is it the sort item? If so, stop searching. Is the middle element too small? Then start looking in the second half of array. Is the middle element too large? Then begin looking in the first half of the array. Repeat the process in the half of the list that should be examined next. So stop when item is found or when there is nowhere else to look and the item has not been found in the array. So this figure shows how to perform binary search. Okay, so you can see this array value are ascending order sorted 15, 26, right? Increasing, okay, value. So the item 45 we want to find. So we have two variables are using first and last. First is the index of the first element. Last is the last searching space. Okay, so we can calculate the midpoint. First plus last divided by 2 is midpoint. Okay, so 0, 9, sum is 9 divided by 2 is 4.5. So we round down. So the 4. So index is 4. And then compare 62 and 45. 45 less, right? So in that case, the searching space is this first, okay, this part, okay, rather than last part, okay. So and then we adjust last. The index is midpoint minus 1, okay. So and then we can this in the second half we can ignore because the first half it may have the value 45, okay. And then we perform calculate the midpoint is set to the sum of first and last divided by 2, right? So 0, 3 divided by 2 is 1.5. Round down, round up, just a round off, right? So we can have one value index, and then this value, this, right? So this one greater, and then we can search, okay, this part, right? This part, and then we adjust the first and the last midpoint, right? Adjust it, right? And then we can perform again so searching, okay. So first last sum divided by 2 is 2, 5, 3 is 5, 5 divided by 2 is 2.5, so we can search it the 2, okay. So okay, and then midpoint here, right? And then compare this one, okay. Oh, this one is greater, so we can search it, this one, okay. And then first last midpoint is the same, and then actually we have only one, right? So 45, 57 different. So in that case we can see the last is okay, midpoint minus 1 eventually. So last, this index less than first index, so which means we cannot find, we can conclude our searching fields. Okay, so found this boolean variable is set to first. Okay, we didn't find, but so we are using this one searching case, not linearly done. So just space here, and a half is reduced, and another half is reduced, another half, right? So this is called searching space is some reduced by 1, exponentially reduced, right? So it is called by binary search. So this is a source code get item. So in that case, we can implement using previous illustration. So midpoint, the first, last index right there, more to search. Okay, first less than or equal to less. As long as this condition holds, so we can keep searching. And the found initialized with the first boolean value, and the more search and the not found, we can calculate midpoint is the sum of first and last indices divided by 2. And so this is an integer, right? So in that case, some integer 0.5 case, 0.5 is we can ignore, remove. Okay, just the integer. Okay, typecast like that, and then switch a statement item and midpoint info element value compared, right? So less, greater, equal. So less case, if this item is less than this midpoint, right? So indicate we search first half, next greater, second half. Okay, equal, we are done. So this is a source code, right? So less, greater, equal, right? So last case we search our first part, right? First half. So we adjust last index midpoint -1, and the more search we can check first index less than or equal to last. We can true case this true. Okay, and the greater case first is set to midpoint +1. We can search. Okay, some is greater than, we can search the second part. Okay, second half. So, and also we can check more to search using this relationship. First should be less than or equal to last. Okay, and the equal case we found. So found flag is set to true, and then item, the info midpoint, the value copy into item, and then we return an item. Okay, so item is returned. Okay, something like that. Also the we are using reference passing, right? So found. Okay, so this one is true or false according to this searching result. Okay, let's move on. Allocation of memory. We have two cases. The first one is static allocation. The second is dynamic allocation. Static allocation is the allocation of memory space at compile time. So we can make execution file. This is a compile time. On the other hand, dynamic allocation is the allocation of memory space at running time, execution time of binary, by using operator new. Three kinds of program data. So static data, automatic data, dynamic data. Static data case, memory allocation exists throughout execution of programs, such as static. This keyword specify long integer see the value. So this case a static value. So this one is exists throughout the execution of the program. Okay, so even though the local variable case, static case, it has a memory. Whenever the code or function, the static value memorizes the value before. Okay, so automatic data case automatically created at function entry resides in activation frame or record of the function and is destroyed when returning from function. This is a local variable case, this one. And the dynamic data case, we can explicitly allocate and deallocate it during program execution by C++ instructions written by programmer using unary operators new and delete. New dynamically allocate memory space, delete is opposite. Okay, dynamically deallocate memory. So arrays created at runtime if memory is available in an area called the free store or heap. So dynamically allocate memory space called heap. Operator new allocates memory for the object or array and returns the address of the pointer to the memory allocated. Otherwise, the null pointer 0 is returned. The dynamically allocated object exists until operator delete destroys it. So object created case, we can create some memory using new. When object is deleted case, okay, also okay, operate delete can delete. Okay, so dynamic array allocation. So let's take a look. Character, okay, pointer PTR. So in that case, we can allocate the array dynamically like this. New character array size 5, and then this one pointer variable point. So the starting address of the first element is 6000. This is 1 2 3 4 5 element. Each one contains a single character. So this one assign means PTR get this 5 character array address. Okay, can get. Okay, so PTR point this one. Okay, and then so we can declare character, okay, pointer type, and the new character 5, this kind of 5 element of character created, and the address is assigned to PTR, and then PTR copy by, so in that case by. Okay, so this one is automatically and the character indicate the end of a string. \0 is indicate the end of a string, and then intentionally PTR PTR or pointer PTR can be subscripted like array. So in that case, PTR itself points the first element of array, and then 0 is the first cell element, 1 is the second, right? So in that case, PTR1 indicate the second element of array, right? So the value is changed with u. Okay, previously y, and then u replaces the value of y, and then we can stand out the out, C out, print out the pointer 2. So this one is we can point out. So maybe this one case pointer, this is one case we can check. Okay, 2 is this one. Maybe this one is 1 is better. Okay, so point we can check the value. Okay, so 2 case 0 1 2, this one. Okay, so if this one is this one, we can see. And class. Okay, so maybe let me correct this one. So we can, if we are using pointer, this instead of 2, we if we using 1, okay, like this, okay, ptr 1. So you can check, so what is the value of ptr 1, okay. So let's move on. Class sorted type character. However, actual our textbook sorted type data is actually item, okay. We can, so but this case we can implement the sorted type using a linked list rather than array. So it has list data. This one is point this the node, okay, node, yeah, pointer, okay. So current position also can be used point out, okay. If we enumerate list items, current post point out current okay searched, okay, element in the list. And left hand side we have the member functions including constructor sorted type and destructor sorted type. So in sort item algorithm for sorted linked list, that is linked list based sorted the list. So find proper position for the new element in the sorted list using 2 pointers such as pred lock and the location. So pred lock is trails behind the that is follows location, okay. So we will see the figures later on. And then obtain a node for insertion and place item in it. Insert the node by adjusting pointers, okay, because we have 2 nodes and the new node is inserted and then point value adjusted to make the link to each other. Increment length because we insert new item. So we have analogy the inch worm effect. So inch worm is a kind of moving like this, okay. Inch worm is here, and then they location of front part, the pred location, you know, the rear part. So first location move, and then pred lock is okay follow, and then it make some arch over loop, and then first moving, and then pred lock also rear part of the following, okay, and the first part the moving and following, something like that. So this movement is called okay inch worm effect, okay. So the list data, this point the first element in the list, okay, and each node linked using this next point, okay. Lila next is null, okay, indicating the end of a list. So second is set a pre-lock to location, pre-lock, and then set location next, okay. So 2 pointers are used to if some new node insert case, location and pre-lock pointer are used. So insert S into a sorted list, okay. So the list data CRX, okay, 3 elements are linked to like this, okay. So location is first, and the pre-log is a null, okay, initially, and then moving, okay, this location, this node next is a location, and the pre-log and the follow location, okay, and then they moving like this, and then this location cannot move further, right? So because the end of list item, and then okay, no more search is set to false, and then this S is created by new operator. So and then we can link pre lock next is this new node, and new node okay, next point to this end of this one, and then we can make so length 4 list is okay, created like this. Okay, so how can two implementations of sorted list be compared? Okay, in terms of okay, insert delete item, some cost. So we saw array-based sorted list, and also we saw linked list-based sorted list. So you guys can compare to each other. Okay, let's move on. So why is a destructor needed? When a local list variable goes out of scope, the memory space for data member list PTR is deallocated. But the nodes to which list pointer points are not deallocated automatically. That is a memory leak by the non-deallocated memory space happens. So we need to prevent this kind of memory leak. So a class destructor is used to deallocate the dynamic memory pointed to by the data member. So in destructor tilde, okay, tilde or tilde unsorted type. So we have the temporal pointer type here. List is a point the start node in the list, right? So this is not null, means still we have a node, right, to search. So list data and the temp data here, okay, this is to delete node, right? And then we can move list data next. List means list is moving to next, okay? And then we delete this one, and then the list node already point the next node, right? So, and then this is not null case. We can still remove something, and then list data temper to remove, right? And then list data next is set to list data to delete next, right? So during this kind of operations, we can delete all list data nodes. So, and then we can okay, safely free memory space allocated for list data. Okay, so the last part this class will discuss object-oriented design methodology. So there are 4 stages to the decomposition process, such as brainstorming, filtering scenarios, and responsibility algorithms. Okay, the first, brainstorming, a group problem solving technique that involves the spontaneous contribution of ideas from all members of the group. Okay, so first, all ideas are potential good ideas. Secondly, think fast and furiously think, actively think, and further later. We can deep thinking later. And then a little humor can be a powerful force for this group brainstorming. So brainstorming is designed to produce a list of candidate classes from some sentences. Okay. So filtering is to determine which are the core classes in the problem spaces through brainstorming. There may be 2 classes in the list that have many common attributes and behaviors. There may be classes that really don't belong to the problem space. In that case, we can ignore those classes. And the scenarios simulate the class interactions. Ask by yourself what if questions. Assign responsibilities to each class. There are 2 kinds of types of responsibilities, knowledge and behavior. So the first one, what a class must know about itself. This is knowledge. What a class must be able to do. This is behavior. Okay. And then responsibility algorithm we can consider. the algorithms must be written for the responsibilities, such as knowledge responsibilities and action responsibilities. Okay, so the first one, knowledge responsibilities, usually just return the content of one of an object variables. Okay, so variable some value returns. Okay, and action responsibilities are a little more complicated. Okay, often involving some calculations. So let's take a look at computer example. Let's repeat the problem solving process to figure out some solution for problem for creating an address list. Brainstorming and filtering. So we have this kind of sentences. Okay, create an address list, blah blah blah. Right. So in that case, we can circle the nouns and underline the verb. Okay, circle noun, underline verb. Okay. And then we can first pass at a list of classes by brainstorming, so we can write down some these kinds of classes based on nouns in the sentences, and then we can delete certain number of nouns non-relevant to our problem solving. So those are important. Okay, and then we can create CRC cards. CRC stands for class, responsibility, and collaboration. This card describe each class. Okay, so class name, superclass, parent class, parent class, or subclass is a child class. Responsibilities, some initialize, itself, the print something, and collaboration is collaboration classes are specified. Name, address, the telephone, email address, right? For describe person information. Okay, and the name. This name also we can have a CRC card. Okay, responsibilities and collaboration. Okay, string type for name. So responsibility algorithms such as initialize and print. So important class object initialize function can be called. Print case each object print function can be called. Okay, so that's all for today's sorted ADT data type. So if you have a question, please let me know. Thank you.